So I've been asked to give some hints on a few of the Turvey problems. These are related rates. And so I'm just going to read over and maybe draw a picture, set you off in the right direction, and then let you finish off these problems. In numbers 3 and 4, a baseball diamond is 90 feet square, not 90 square feet. What that means is it's basically a square that's turned sideways. Oops, let me get my pen going here. And each of the sides is 90 feet. You can think of those as the base paths. So 90, 90, 90, 90. Okay? And those are right angles because this is a square. So this is our baseball diamond. You can think of the bases as the little right angle marks. Coach Jack Handley runs from first base to second base at 60 feet per second. How fast is he moving away from home plate when he is 30 feet from his base? So this dude, Coach Handley, starts off at first base and heads towards second base, right? And so he's moving in that direction. So that's what I'm going to do. I'm going to put an arrow there because his distance is changing. And they mentioned the distance from him to home base, which would be this distance here, and that is also changing, right? Like it's getting longer. So anything that's changing, we want to put a variable on there. So for Coach, I'm going to put an X to represent the distance that he is moving from first base to second base. And the other distance that's changing is this hypotenuse here. And since I'm, a little narcissistic, I'm going to put M for Murphy here. And so that's another measurement that's changing. Okay, now let's get some information organized underneath here because they mentioned some rates. So first of all, Coach is moving from first to second at a rate of 25 feet per second. And even though it doesn't say at a rate, it does show me a rate, right? Feet per second. So that tells me that this 25 feet per second here is a derivative. It's the rate at which x is changing with respect to time. So dx over dt equals 25. And that's positive because x is getting longer. Our question is, how fast is he moving away from home plate when he is 30 feet from the base? So when he's 30 feet from the base, that is x equals 30. And how fast is he moving away from home plate? Oh, yeah, okay, so I had it right. They're asking us, this is what we're trying to find, dm over dt. How fast is he moving away from home plate? How fast is m growing, right? So this is the thing we're trying to find. And so to answer problem 3, we're going to use the triangle that I drew here. Its measurements are 90, x, and m, and you're going to write an equation relating x and m so that you can take the derivative and plug in the numbers I've listed here. That's for number 3. For number 4, it says, how fast is he moving away from home plate when he is 45 feet from first base? So for number 4, we're going to do a new set of measurements. We're going to say x equals 45. But his pace is still the same, so dx over dt is still 25. And then we want to find dm over dt. So the only thing that's really changed here is the numbers that we'll plug in. The formula is going to be the same and your derivative is going to be the same. So I'm going to leave you to finish this off. Use this triangle that we've drawn to write a formula that relates x and m. After you write out the formula, take the derivative, plug in the numbers, use these numbers for number 3 and use these for number 4, and you should be able to answer those 2 questions. That's my hint for that one. See if you can finish it off. Let's take a look at another problem. In 10 and 11, a fish is being reeled in at a rate of 2 meters per second. That is, the fishing line is being shortened by 2 meters per second. So what we're saying is this thing is getting shorter, and that rate is 2 meters per second. So negative 2 meters per second because it says shortened. Okay. If the fisherwoman is sitting on the dock 30 meters above the water, how fast is the fish moving through the water when the line is 50 meters long? That's for problem 10. Problem 11, how fast is the fish moving when the line is 31 meters long? And that's for problem 10. And we're going to put our answers in meters per second. So we are looking for how fast the fish is moving through the water, and the fish will be moving in this direction. So essentially, we need to think of this question also as a triangle. And it really doesn't matter if that fish is underwater or not, because whatever speed the fish is moving in this direction, this line is also moving in that direction. So the picture that you really want to draw, even though I know they gave us a picture, is that the fisherwoman is 30 feet in the air. That's a constant, so I can put that on my picture. The length of the hypotenuse, which is the fishing line, that's changing. So I'm going to call that X. And the fish itself, the distance from the fish to the dock, is also changing because the fish is moving this way. And so I'll just call that F. And now we have a triangle again. And actually, we're going to use the same equation for this example that I hope you did in the other example. But, it's that famous equation from geometry class that everybody remembers. But that'll relate these variables. And then let's just get organized at what we have in the information. So we're given that the line is being shortened by 2 meters per second. So that is dx dt. And that answer is negative 2 meters per second. We are told for number 10 that the line itself is 50 meters long, right? So that would be x. And what we are trying to find is the speed that the fish is moving, right? And so we're looking for df dt. Now, you're probably going to come across a situation where you need a measurement for f, right? I don't have f listed anywhere here, but at this moment in time when x is 50, you can solve for f. So you'll figure out f so that you can then eventually solve for df dt. In number 10, the only thing you're changing is you're changing the x. So instead of x equals 50, for number 10, you'll do x equals 31, and then you'll have to get a new f, right? So you'll have to use that equation to solve for f. So you'll have 30, and you'll know that x is 31, and you'll solve for f, and you'll know that number. And then again, you can plug those into your derivative equation, the one that you came up with after you did the implicit differentiation. So think of the picture as this triangle, 30 feet on the vertical leg. Call the horizontal leg F and call the hypotenuse X. That's the fishing line. And then you can set up the same type of situation as the last problem. Got one more set of hints for you, then we'll cancel this video. Not cancel it. We'll, wrap it up. Whatever you call it. It's been a long day. So in number 14, oil is spilling into Lake Winchester in a circular pattern. If the radius of the circle is increasing at a rate of 3 feet per minute, how fast is the area of the spill increasing at the end of 10 minutes? So first of all, this is very similar to a problem that we talked about in class. We've got a circular region. This time it's oil instead of water. And that circle's getting bigger, right? The spill is increasing. So this is going out in that direction. The radius is increasing at a constant rate of 3 feet per minute. So, whoa, baby. I just did a weird thing where I moved all that stuff over here. Let's see if we can. All right. So that's the radius. So we'll call the radius r because the r is growing, but the rate is 3 feet per minute. So dr dt is 3 feet per minute. And we are asked to find out how fast the area of the spill is increasing at 10 minutes. So we're trying to find area, which would be dA dt, the rate at which the area is increasing. To me, that means this is a typo. We should be expressing our answer in terms of feet squared per minute if we're looking at how fast the area is changing. Now, we don't really have area represented on our picture, but this is the area of the circle. That we'll call that letter A. And I just need a formula that relates A and R. So use your famous formula for the area of a circle. You'll write it out. You'll take the derivative. And then you'll plug in 3 for dr dt. And then, at the end of 10 minutes, mamma mia. Aha. Could you tell in the video that the light bulb just popped on in my head after that long pause? I'm not even going to edit this thing. So since the radius is increasing at a constant rate of 3 feet per minute, how long is the radius after 10 minutes? All right, so that's the other thing that you're going to have to figure out, because we're going to need a value for R. We're trying to find dA dt. But your job will be to get a value for R, because you know that it's growing 3 feet per minute after 10 minutes. How long is it? Put that number here. Then do your equation. Take the derivative. Plug in 3 and this number. And then you'll be able to solve for dA dt. See if you can get it. I like this problem because it made me think. Because rather than tell us the radius, they are just telling us how long it took to get to that measurement. So that's clever, but we can handle this. We got this, all right? Give it a go. Let me know if you have any other questions, and enjoy the rest of your night. Take care.